I apologize for the interruption, everyone. Please bear with me for a moment. My son unexpectedly entered the room, and I need to address this situation briefly. Thank you for your understanding and patience during this minor disruption. Here, the change in value is very important, as it indicates whether you have increased or decreased your value. If you increase it, your value is high. And if you decrease it, your MX, by transverse magnetization, is affected. So, if you reduce the flip angle, what will happen is that at that moment, you will have retained a large amount of a certain quantity, and the percentage that will decrease will be minimal at a specific point. What is the name of this curve, doctor? The signal means that it decreases and weakens. Why does this happen? It occurs as a result of the finessing that happens to protons in the X and Y axis. The result of the finessing that occurs to protons in the X and Y axis, the signal amplitude weakens because, over time, dephasing increases, causing the signal to diminish, which means the protons in the X and Y axis move in this manner. As this continues, dephasing increases, and the signal it provides in the transverse plane weakens. The curve appears to drop, giving the impression that it is continuously decreasing, experiencing damping until it reaches zero. In the gradient, what exactly do you want to do? You definitely want to strengthen the signal here because it has weakened significantly. So you use what works best, and then you use whatever is available to start capturing your signal effectively. This is the form of gradient echo imaging or gradient image, as we see, of course, as estimated by the gradient sequence and its applications and uses. Of course, yes, as I moved, of course, I am certainly able to use the gradient sequences and its practical applications and its utilizations. Yes, of course, here it depends if, for example, you have a hemorrhage or a certain pathology, and this pathology that exists has made homogeneity in the magnetic field or makes magnetic substability present, then this will be more prominent with you in the gradient sequence for you. Okay. There is an important point when we enter the topic of MR and geography. Did we understand that the topic of the gradient as a sequence is fast or slow? Fast. Secret. Indeed, as you might already know, the gradient sequences are crucial in many scenarios. For instance, as an illustration, when dealing with certain pathologies, the effects become more pronounced. Absolutely, this is a key aspect to consider. Okay. As is well understood, there is an important point when we enter the topic of MR and geography. Did we understand that the topic of the gradient as a sequence is fast or slow? Fast. Secret. What I'm pointing to with the yellow arrow, what is that? A vessel. Okay. Is it appearing in black or white? Black. So does that mean I'm getting a signal from it or not? Is my signal here strong or weak coming from this vessel? All right. Why does the vessels appear in the spin echo sequence in black? It appears to you in black like that. Why does it appear in this color? Why does it appear in this color? Today, I am starting, guys, with the 90-degree pulse, and then I will start with the 180. The whole idea is quite simple. It involves the plot flowing, right? Yes, the plot flow. Now, I have come here and given your 90-degree pulse, and there is a vessel where the red blood cells, RBCs, are flowing. In the blood, RBCs contain hydrogen atoms, and these protons should be treated like the rest of the tissues and the surrounding noise without any issues. So today, when you give your scan, what do? You perform your slice, the section you are taking from the patient. During the 90-degree pulse in this slice, there may be a group of RBCs or blood present in these sections, whether in an artery or a vessel. Whatever the artery or vein is, these RBCs or the flowing blood are exposed to the 90-degree pulse along with the surrounding tissues. So what should happen? There should be slow excitation. It has the same longitudinal relaxation we were discussing. No problems there. However, what happens is that the blood itself is moving. If I have chosen a specific slice, when I apply the 180-degree pulse, should I apply it in the same slice or in a different one? In another segment, not in the same segment, but the blood is where it has moved to a new place, right? This new one, let's pay attention. Everyone. I worked on this slice, so the magnetization of this segment has all dropped. It has become in the line and has dropped into the X and Y. Am I going to give the 180-degree pulse to provide refocusing for the pulse? Essentially, the protons, which are a new entry, have longitudinal magnetization with the Z-axis. So when I give them the 180-degree pulse, I will be giving a signal. But this won't give me a signal, because at that time, you will flip it to the other side in the Z direction. So, who am I working with here? If, for example, I am imaging a T2 image, I want to work on transverse magnetization to give it a 180-degree pulse. But will I find the initial red blood cells, RBCs, present or not? They are not there. So will the new entry be affected? Will it give me a signal? What will its signal be? It won't give me a signal at all. That's what will happen, which is why the image appears this way. The image appears dark, or the blood vessel has become dark, which is called a flow void. When you take any spin echo sequence with any fluid that is moving quickly, faster than the 180-degree pulse, and faster than your echo time that you are recording, it has moved from its position. So, in this new place, what will it give you? It will give you a weak signal. So it appears this way. This means that if I have a vessel in the spin echo sequence, like the jugular vein, for example, if its blood flow is slow and gives me a signal, you might detect if there is even stenosis or a specific pathology causing the blood flow to slow down. You can benefit from this property or the information you obtained in your diagnosis. The whole idea of the flow void is that the blood has moved from its place, so the signal reached the blood in this way. This is in the spin echo. This technique can be relied upon in the process of MRI angiography because you can image the arteries in this way or the plaque. After that, you can perform something called the subtraction technique, which subtracts the existing tissue from the blood vessel and provides you with images. But in reality, they rely more on the time of flight. What is this time of flight? We have a problem with that. The second point I want to mention is about the protons. They are moving. It's moving correctly. And as it moves, I'm applying the phase encoding gradient. This phase encoding gradient will cause these protons, which are moving, to pass through different areas of the gradient. The different areas in the gradient will make the frequency of the precession different. So what should I do? For example, I apply a specific gradient to my gradient. If my gradient is applied in the same direction as the flow of my blood vessel, it means it's moving with me in this way. It starts with the movement of the area here, which is not fixed, and how the tissues are at a certain point. No, They are constantly moving, and this change causes them to lose the signal that was created. This is what they call, as you are with me here. The blood vessels, or your arteries, due to their movement, are exposed to the phase encoding gradient. This movement causes a change in your precession frequency, which leads to signal loss or a loss of magnetization, resulting in a dark signal. You have the spin phase effect and the flow void that I mentioned earlier, which is essentially the movement of the arteries from my slices and the new entry in their place. This affects the spin echo image and makes the blood vessels appear in your dark color. For example, here, in the femoral artery, it appears black due to the same reasons we discussed earlier. This can clarify the topic for you. Here you are applying a 90-degree RF pulse. This 90-degree pulse is applied in all these slices. They all experience excitation. The exposed part is the one that gets excited. This is the three that the flow coming from outside and entering its slices is unexposed. Right? What will happen? The one that was exposed, which was the RF pulse, has now flowed out of its slices and entered a new place in this case. There is no signal because it is not actually affected. I see a dark signal, guys. The techniques or methods depend on producing black plots and in the spin echo sequence. Now, let's talk about the time of flight. So now, if I take this out of the topic and use fast or slow. Fast. Fast. Okay, but I want to make the visualization, guys, light up like the color of the arteries, for example. So what do we want to think about doing? They said, what do we do now? They said there is something called, what does steady state mean? They tell you that now, when you give your RF pulse, what happens is recovery after 90. If you are using a long TR like spin echo, for example, it achieves full recovery. Like the L, it starts to revert. It connects to the area that is the baseline or close to its value. But if your TR is slightly short, like a gradient, will the signal return to full recovery or not? God will not let you down. He will open doors for you. It won't be long, because what will happen is that He will come back and say that you have initiated a new TR, and it affects you to bring it down again. He will come back and affect you, creating a state called steady state. What is steady state? It is a constant value for MZ, resulting from applying short TR. Short RF pulses, which means the recovery of T1 or longitudinal magnetization does not achieve full recovery. It reaches a certain point and stabilizes. This is the steady state for you. So you name this area as if you have done saturation. They call it steady state or steady state saturation. Now you want to know why this is said to give you a stronger signal than long TR. What does this mean? With short flip angles and the gradient, it gives you a higher signal. How? I want to understand what you are saying first. I am applying an RF pulse. I will wait a long time and then give you another RF pulse. Logically, based on what we were explaining, a high value of longitudinal magnetization should give you a stronger signal, right or wrong? This is what we were saying, the value of magnetization, and which one shows prominently because it is higher in magnetization, inducing a higher current in the coil, resulting in a higher brightness signal. Therefore, this signal would be higher than the signal I would get from the steady state. However, the steady state tells you that there is something you are not paying attention to. It says that something happens here when you come with a 90-degree RF pulse, and this leads to a division. It undergoes recovery and returns to a certain level. And then you start applying another RF pulse, because, keep in mind, the longitudinal magnetization, MZ, here is coming from 0. I am talking about a large flip angle of 90 degrees. No matter what, even if your TR is long, the recovery time will not return to a high value. It will need approximately 4 to 5 times the T1 constant value of the tissue to achieve full recovery. This means that for the tissue to return and achieve full recovery, you need to multiply the T1 value by 5. If it was 0, then when you apply the second RF pulse, it will drop again, and you will find that your longitudinal magnetization value with a 90-degree pulse will not recover significantly, so the signal will be low in case you are using a small flip angle. When we apply the second RF pulse, the recovery will reach a higher area. Even if you are using a short TR, but it hasn't fully dropped in the transverse plane yet. So when you apply the second RF pulse, its value will be close to the true value at full recovery, unlike here, where it was far from the true value because it was starting from 0. Therefore, the steady state here gives you a higher signal with a small flip angle compared to a 90-degree pulse. What I want to say is that we will use this in angiography. How exactly? You ultimately want to achieve your goal of successfully reaching a steady state. I want to effectively use a small flip angle and a gradient to conduct a quick examination to image the arteries and make them bright. So, do I want to make the signal of the arteries higher or lower than the surrounding tissues? Higher? Great. So what should I do to make the signal of the tissues surrounding the arteries lower? They said to bring it to a state of least disturbance. How? By giving it a series of preparation RF pulses before your examination. What do these RF pulses do? They said they will make the magnetization of all these tissues reach a state along the path we are doing, exactly a small angle, and you give RF pulse, RF pulse, RF pulse. So the value of longitudinal magnetization for the tissues here at this point. So what does that mean? Then you will have the new area, the longitudinal magnetization of this new area. The value itself will be higher or lower than the state-state magnetization. So, you see, you have made a difference between the new area that has entered and the existing tissues, right? The new area that has entered will be captured in the imaging. Why? Because it won't escape. No, it won't escape. Why won't it escape? Because your sequence is short. Your sequence is short. You don't have 180-degree pulses and all that. You are using the gradient continuously with a small angle. So, at that moment, when you give it a 90-degree pulse, it will find that the magnetization value of all the tissues here is low, while the area here is different. So when it goes down and comes up, which one will give you a strong signal? The area will start to appear bright and you will see that area illuminated. When you come here, what are you doing? You are applying repetitive short TRs to create a saturation band. Do you remember the topic? If you go and focus on MR, they will tell you to create a saturation band. What does saturation band mean? It means you are applying a series of RF pulses to suppress the signal from certain tissues, so the limitation of that signal will be less than its original value. The remaining tissues are always told to place the saturation band in the area where there is a signal. For example, if you have cerebral angiography, you are advised to place it in that area and underneath. This is to cancel out the signal if it is coming from the background or if there is a signal present. The meaning of this saturation band is that you are applying a set of RF pulses that cause the signal in that area to drop, making the free area less than the area of interest that you want to work on, thus enhancing the signal coming from the area of interest. This results in a better or higher signal compared to the other tissues. This is what happens. Is this approximately correct? And what about all the tissues present? What happens to the unexposed area where the new background is? The old background will exit, but will the tissues exit or remain as they are? They will remain as they are. So the longitudinal magnetization of these tissues is less than that of the new background, which enters with its new magnetization. Because it recognizes the same magnetic field, it starts to give you a brighter signal compared to the existing background. So the arteries appear to you in this way. I call this the time of life. I hope you understood. Thank you, Lord of the worlds. Is Islam appearing happy?
Okay, but there was another point, and they were saying that in the gradient, it excites the spins inside the slab and those outside the slab. That's why they turn off the light, unlike spin echo, which excites at 90% and 180% inside the slab. So it can take this or that, which is why it becomes flow related. You mean that in the time of light here, it works again like this? Sorry. The time of light has approximately two methods. The first method that you explained is the one with 90 and 180 flow void, right? The flow void will only give you dark images. There are two conditions that give dark images because the 90 and 180 are in the same slab. There is a gradient that excites the slab and what is outside the slab, meaning even the blood that hasn't arrived yet. How does he repeat the experiment? They say that he repeats the experiment on the whole body.
No. It is what happens, like you said. The whole idea is that you choose this segment or this specific segment of yours. Okay? The flow void that is inside it, this is before the sequence itself, Dr. Islam.
I understand, sir. I understand. This is the second method. The first one is the ingredient that causes excitation inside and outside. That's why the heavy substance is subjected to refusing, and everyone wants it. So it gives dexamethasone. Yes, yes. This information is even written down. I have written it in the notes I am working on. It is written in the part that is about this specific detail, and it is written in the real part, which is noted in the cave.
Yes. No. It's present in the question and answers related to MRI. The problem is, you're trying to piece things together. There isn't a book or reference for MRI. The part you memorized, I explained it now. The part I didn't understand, thank God, here are the doctors. So, regarding the MRI topic, you completely comprehend fully how the image works and how things are going with the time of light and the spin echo or flow void, and these things are clear for you in great detail and thoroughly. The point I want to make is that we are supposed to, in a comprehensive manner. In this part, we are supposed to discuss the time of light, the first spin echo, and inversion recovery. The MRI technique relies either on dark blood or bright blood. In bright blood, the contrast agent gadolinium is used effectively. We talked about the gadolinium cycles, and I even shared a video I made on my YouTube channel explaining gadolinium in more detail. You will find more details there, even better than what I presented in the lecture with you. I also hope you will check it out. You will see that I delved a bit into the chemical area related to gadolinium. The gadolinium has 7 unpaired electrons. The last level of gadolinium consists of 7 electrons, each of which is unpaired. What does that mean? I am referring to something in the energy levels of the atom called orbitals. Each energy level has a set of orbitals, which are like slots where the electrons reside. The electron is located in this force in this symbol. So every force located in 2 beds involves 2 electrons. If there are 2 electrons sitting in each force, this is called the electron pair, meaning both are resting on their beds and each one moves in a certain direction, creating a magnetic field from the electron and interacting with the magnetic field from another electron because the electron is charged. The magnetic field created by these electrons is approximately around